Question 2 looks like this, and the question wants us to find angle BCD. So it wants us to find this angle. We've only got this one at the moment. To find this angle, it would be really useful to have this angle, because angles at the centre, subtended from the same arc, are double angles at the circumference. So if we can find this angle, we can find this angle. It would be difficult to find this angle from this angle. It's not a cyclic quadrilateral because this point is outside of the circle. And this does form a quadrilateral, but we don't know the size of these two angles, so that doesn't help very much. So what we want to do really is, to start with, we're going to ignore that part of the diagram, and we're just going to work with this quadrilateral here, which is very similar to the quadrilateral in the last question. We've got a radius and a tangent, so that is 90. We've got a radius and a tangent, so that is 90. That means these two angles in this quadrilateral add to 180. So these two angles must also add to 180, making this one 130 degrees. Now we apply the circle theorem. The angle at the centre is twice the angle at the circumference when they're subtended from the same arc or chord. So this one must be half of this one, so that angle is 65 degrees. Question 3 looks like this, and we want to find angle DOA. So this is the angle that we're trying to find. Now, I've said before, with these circle questions, there's not only one way of doing it. So if you've done this question and you've got the right answer, but you haven't used quite the same method as me, that is fine, as long as what you've done makes mathematical sense. So if you have applied circle theorems correctly and you've ended up with the correct answer, that is fine. The way that I would do this one is, I'm going to mark in all the angles that I can find straight away. So I know that this is 90 degrees, and I know that this is 90 degrees because these are radii and tangents. That means for this triangle, I can work out this angle here, because angles in a triangle add to 180. So this angle here is going to be 180 minus 90, so left with 90, minus 34, so 56 degrees. These two triangles, so this one and this one, are going to be congruent because they've got two sides the same. Actually, they've got three sides the same. This one is the same as this one because they're both radius. Tangents which meet at a point are the same length. So this one is the same length as this one. And then they share this hypotenuse here. So those must be the same as well because it's the same length. So these are actually congruent triangles because they've got three sides the same as each other. That means that this angle here will also be 34 degrees, which means that this angle here must also be 56 degrees. So now we can find this angle here, DOA, by doing angles on a straight line. So this is a straight line, this is the diameter. So this angle here will be 180 minus these two angles, so minus 56, minus 56. I wish you were here to help me with the math. You know I get stuck on these bits. So 180 minus 112 is 68 degrees. Question 4 looks like this, and it wants us to work out the size of angle ODC. So it wants us to work out this angle here. Now it is tempting to just say that that angle is 75 because this looks like the alternate angle theorem, alternate segment theorem, sorry. But this would need to be a straight line for that to be the case. So we can't use the alternate segment theorem yet, from what I can tell. So we know from the previous questions that a radius and a tangent, that is 90 and that is 90, So this angle here plus that one makes 180 because angles in a quadrilateral in total make 360. You've got 180 from these two right angles, so you need another 180 from these two angles here. That makes this one 140 degrees. Now another thing that we know is that this radius and this tangent makes 90 degrees here. So this angle here needs to add to 75 to make 90. So this is 15 degrees. I'm going to split this by adding in another radius. I've now got an isosceles triangle here. These are the same length, and base angles in an isosceles triangle add to 15 degrees. This side is also the same length as this because it's a radius, which means this angle that I want to find and this angle are the same because they are base angles in an isosceles triangle. Final piece of the puzzle then. If I find this angle, I've found this angle. Angles at the centre are double angles at the circumference when they've come from the same 2 points. So this full angle here has to be half of this angle here. So that full angle must be 70 degrees. But this little blue bit is 15 degrees. So the red angle must be the whole angle, 70. Subtract that 15, which gives us 55 degrees. So this angle is 55 degrees, which means this angle is also 55 degrees. Again, you might have done this a different way. If you have, that's absolutely fine, as long as you've reached the answer of 55 degrees and you've used circle theorems, properties of triangles, anything mathematically sound to work it out. If you put this line in and you say it's cut it in half, no, it absolutely has not. Equally, this angle here and this angle here, as you can see, definitely not the same. Question 5 looks like this. Now, this looks like quite a horrible question. There's a lot going on in it. There's a lot of different shapes in it that we could start working out angles for. So, having a look at this, this is the angle that we want to find, DAC. So we want to find this angle here. Now, what immediately strikes me about this is that this red angle plus the 25 we already know sits in this big triangle. This red angle here sits in this triangle here. So can I use either of those things to make this question easy? Well, I'm going to fill in a couple of angles that I can immediately fill in from what I've got already. So I've got this 100 degrees here and it's on a straight line. Angles on a straight line, add to 180. So this angle here is 80 degrees. Now, this 80 degrees lies in this triangle. I want this angle. So if I can find this angle, then I can take these two away from 180 and I'll end up with that. So how could I find this angle? This angle is at the circumference and it's subtended from these 2 points here. If I could find the angle at the centre subtended from these 2 points here, I'd be able to halve it and that would give me that one. This line does not go through the centre at the moment, so I'm going to add in that centre line instead. Okay, I've got an isosceles triangle. This bit and this bit are both radii, which means that this base angle and this base angle are the same. They're both 25. So this angle at the centre here must be 180, because angles in a triangle add to 180, minus 50, 25 plus 25. This angle at the centre, subtended from these 2 points, is 130. Then taking these 2 points to the circumference, this angle is half of that, so it is 65 degrees. So angles at the centre are double angles at the circumference. They're subtended from the same 2 points, and they are A and B meet at the centre to make this angle of 130. A and B meet at point D to make 65. So now I've just got a triangle here where we've got two of the angles. We've got 80 and 65. So this angle that we're after is going to be 180 minus 80 minus 65. So 180 minus 80, 100, 40, 35 degrees. So this angle that we're looking for is 35 degrees. And so we haven't actually had to populate anything in here. You might have been tempted to do vertically opposite angles or 100. That's absolutely fine. I wouldn't have used it in my solution, but if you have used other angle properties and you've got an answer of 35 degrees, then you are correct.